In this section, we're going to talk about composing linear transformations and the inverses of linear transformations. So let's first talk about composition. Okay, so suppose we have two linear transformations. So one linear transformation T transforms vectors from a vector space U into a vector space V. And another linear transformation S maps vectors from a vector space V into a vector space W. Notice, by the way, the output of transformation T, the codomain, is the same as the domain of vector space S. Okay? The composition of the two transformations S and T is the transformation S compose T. We use this little open circle to mean composition. So S compose T that goes from U, the domain of T, and it maps that into W, the codomain of S. And the way we define it is that S compose T of a vector is equal to S of T of U. So what we're doing here is we're plugging U in to T. T maps that vector into V. And then once we have a vector in V, we plug that into the domain for S. And then that maps it into W. Okay? So we're just applying two functions, one right after the other. First, we apply T, and then we take our output there and plug it into S. Okay? So let's consider two linear transformations. Let's look at an example here. We have two linear transformations. The first is S. It maps R2 into R2. And then the second transformation is T. And it maps R3 into R2. And here's how they are defined. Okay? We want to find the composition of S with T. So notice, by the way, we know that S compose T, the input is going to be R3, right? Because S compose T is equal of a vector is equal to S of T of the vector, right? So the first vector gets plugged into X or into transformation T. So that means it needs to be a three-dimensional vector. Then we apply transformation T. And when we apply transformation T, it maps the vector into R2. So now it's a two-dimensional vector by the time we apply transformation T. And then we plug that into transformation S. And S maps two-dimensional vectors into other two-dimensional vectors. So S compose T is going to, we start with a vector in R3, and then by the time we're all done applying everything, we end up with a vector in R2. Okay? So we want to find an actual expression for this composed transformation. So we know S compose T of xy, xyz. We're plugging in three-dimensional vector. xyz. By definition of transformation, that's going to be S of T of xyz. Okay, so we first plug our vector into T. And we can see that if we plug xyz into transformation T, then the transformation of vector xyz, which is exactly what I have here, is a two-component vector. The first component is y plus z. The second component is x. So I'm just going to plug that in right here. S of y plus z x. Okay? Next, we want to find S of y plus z x. So here, this tells me the rules for plugging something into transformation S. X is whatever the first component is that I'm plugging in. Y is whatever the second component is that I'm plugging in. So in this case, The y plus z, that gets plugged in place of the x because it's my first component. So every time I see an x in this expression, this vector, I plug in my first component, y plus z. Okay? And y is the second component, so every time I see a y in this expression, I plug in my second component. Second component I'm plugging in this case is x. Okay? So let's see. My first row, it should be first component plus 2 times the second component of the input. So first component plus 2 times the second component. Okay? And the second component of the output is going to be 2 times the first component of the output minus the second component of the, 2 times the second component of the input minus the second component of the input. Okay, so 2 times the first component of the input, which is y plus z, minus the second component of the input. Okay, and so that's the transformation. I could maybe tidy it up just a little bit. 2x plus y plus z and negative x plus 2y plus 2z. Okay, that's the composition. That's what I would get if I first apply transformation t to a three component vector, the three-dimensional vector, and then take the result and apply transformation s. This is the final result of doing all of those operations. This is the composition of the two transformations. And we have the following theorem about composition of transformations. The composition of two linear transformations is also linear. So that would certainly be the case in this previous example. We have two linear transformations. S is a linear transformation. T is a linear transformation. The problem tells us that. Okay? And so therefore, the composition of S and T is also a linear transformation by this theorem here. If we compose two linear transformations, the resulting transformation is also linear. All right, so let's prove it. The proof is pretty straightforward. We're going to take two transformations, T and S. We need to show that the composition is linear. So remember, to show that a transformation is linear, you need to show two things. So for some transformation, I'm going to call it R, so just so we don't confuse it with the letters we've already used, S and T. So if I have some transformation R, if it's linear, and I multiply and I take the transformation of a vector, of a scalar multiple of a vector, it doesn't matter if I take the scalar multiple before or after I apply the transformation. Okay, so that's the first condition that a linear transformation must have. The second condition is that if I take a sum of vectors and then take the transformation, that's the same as taking the transformation first, then taking the sum. Okay, so generally we have to check both conditions. Now, this proves very clever because they actually check both these conditions at once. So they need to show that both of these conditions are true for the composition S compose T, for the new function we get after we compose the functions together. Okay, and so instead of looking at both of these conditions one at a time, they look at them together by taking a linear combination of two vectors in the domain of the composition, which would be vector space U. Okay, so we take two vectors, U1 and U2 and U, and two scalars, A and B. Okay. And so let's go through their argument, and then we'll show why both of these conditions are satisfied. Okay. So they have the composition of a linear combination of two vectors, U1 and U2. All right. Remember, composition just means we apply each function one at a time. So first, I take my linear combination and I apply t. And then once I'm done with that, I take the output and I apply linear transformation S. But t is a linear transformation, right? And for linear transformation, just focusing on the inside here, we know that we can split the transformation up over the addition and then pull out the scalars from the transformation. Okay? So now we have S, and then inside function linear transformation S, we are plugging in a linear transformation, right? A times one vector, whatever the transformation of U1 is, it'll be a vector, plus B, some constant, times another vector. The transformation of U2 is whatever vector that is. Okay? Because we are taking a linear, because we're plugging in a linear combination into a linear transformation, we could do the same thing again. Okay? That is, split up the linear combination over addition, pull out the scalar multiples. And then S of t of U1 is just the composition of S and t with U1 plugged in. S of t of U2 is just the composition of S and t with U2 plugged in. And so we were able to pull out the scalars and split over addition. Okay, so what we've done is we've kind of checked both these conditions at once, right? Because if we choose, say, b equals 0, then that goes away, and we've shown condition 1. And if we take the case where a and b both equal to 1, then that would be equivalent to this condition here. So showing this, that the linear combinations are preserved, it is equivalent to showing that both of these properties. So in summary, what this proof is showing us is that if we have two linear transformations and we take the composition of those two linear transformations, the resulting composition is also a linear transformation.